to start by sharing that because there are some people that traveled from our meetup groups in Zurich. Reto, I know you're sitting in the back. Thank you for coming. From Berlin, from San Francisco, and so thank you for making the trip and wanting to learn more about our technology and really be part of our community. This is our lives for us. We take this great pride into what we do, and it's genuinely an honor to spend the next 30 minutes, 45 minutes, depending on how I do, comparing Grackle to SQL. And before I start diving into the topic, and I've got a clicker, I just want to start with a small story, if that's okay. So, in 1970, so this is 50 years ago already, there was an idea, a paper that was published by someone that we at least look up to very, very much, a guy named Edgar Codd. It was called TED amongst his friends. And TED basically introduced the idea for relational algebra and relational calculus in this specific paper. There's a number of papers, but this was the first one that was made publicly available. And the relational algebra and relational calculus were two languages that were built to effectively express and work with complex data, make it easier. Edgar Codd himself, the paper itself makes only one citation to set theory by David Childs from a couple of years before that. But at the time when it came out, it was still fairly obscure, and Ted worked at the IBM research facilities in San Jose. But the paper got traction in the community. People started to talk about it, started to come together, and Ted eventually formed the research group called the System R group, R standing for relational. And the System R group basically made Ted's ideas, elaborated them further, and more papers were published to eventually come together and create an actual database management system based on the relational model. But in TED, because back then databases were primarily just built based on navigational databases, network databases, hierarchical databases, where if you wanted to write a query to the database, you needed to know the physical way of how your data is stored. So there's inherent complexity in doing that. And so Ted would ask his team, he would say, sure, you can express a question by writing a navigational plan, but the navigational plan is not the essence of what you're trying to accomplish. So would it not be nice if you could express the question at a higher level and let the system figure out how to do the navigation? This quote is really, really interesting. And it's effectively ties into the history of how we innovate in computer science. And I'm going to come back to it later in my talk, but I want to start off with this idea because it's very close to how our hearts and how we conduct our engineering on a day-by-day. Now, the problem with Ted's ideas were that they were steeped in mathematical formalism, steeped in mathematical notations, so they were rather complex. And hi, Samuel. And so two, I guess, visionaries of the System R team published a paper that eventually came to be the first introduction to SQL. At the time, it was called SEQUEL. That SQL notation, actually, there was a trademark by some aerospace company in Britain, so they had to change it to SQL, but we did get stuck with the term SQL. But the fascinating thing about SQL and why it stuck is because it made Ted's ideas simpler. It made them look simpler. The ideas were the same, but it made them look simpler because the language was steeped in English words. So users that weren't necessarily familiar with mathematical notation and symbolisms were suddenly able to have access to this powerful model under the hood. So, just to fast forward to now, relational eventually to become the standard of how we innovate and how we build software. Oracle beat IBM to market with the first commercial relational database and grew to what it became today. And now, as the title suggests of this talk, I'm not going to be speaking just about SQL, but I want to specifically use that as a reference point to describe our language, Grackle, which for some of those that aren't familiar, I hope you've had some form of introduction to the language and some of the basic syntax. And with that, I would also say that as I go through the slides, I'll be focusing primarily just on SQL and not on the relational model. And for those of you who don't know, SQL, as alluded to just now, SQL is just the implementation, the language that implements the relational model under the hood, but the relational model itself is independent of any implementation that goes above it. And that's really important. So for the purpose of this talk, we're just going to be focusing on the language, not on the actual algebra, the relational algebra, or the relational calculus. However much I know some here in the audience get very excited by that. Heiko, I know you are. So this sentence describes quite well the value of what SQL gives to us, at least when it came out. So the quote reads, "A language that you can read and understand intuitively enables you to ask questions at a higher level while letting the system figure out how to do the lower level operations." There's three components that I want to zoom into this sentence, which are very interesting. The first is a language that you can read and understand intuitively. We can say a language is as such if it has some form of strong relation or semblance with natural language. We say that a language allows you to ask questions at a higher level, which means you can instruct the computer to do some higher level operations while effectively letting the system figure out the lower level implementations. Now, effectively, that's what SQL, with its relational model, did. It abstracted away lower level operations, specifically the whole navigational plan. And I hope by the end of this talk, and definitely by the end of today, I hope you understand that that's a similar idea of how we're building and how we're creating a new language in the form of Grackle. And by the way, this isn't particularly novel. This is just how computer science, the field, moves ahead and how ultimately we change the world by doing this. So let's dive in. And first, I want to make a caveat. SQL has been around for 50 years, so it would be rather unfair to make it comparison directly with a language that's only been in development for 4 years. So if you can appreciate that as a caveat. So there's three things that I want to talk about today. So first, we're going to be looking at the conceptual data model. How do we think about creating our models in Grackle and in SQL? Then we're going to be talking about how do we write and read using a relational mindset to the database, and then comparing different types of operations. I'm just going to be covering standard SQL operations, and then look how we would think about these questions in SQL as well. And finally, with that in mind, then we're going to step out of the relational world and actually look at how and why you should think about Grackle and what are the types of queries that would benefit you from using Grackle itself. So let's dive into. So this is a nice, I hope most of you are familiar with this ER diagram, or just generally ER diagram modeling. Heiko already mentioned it in this talk, but it's a form of modeling that was introduced by Chen, which has become ubiquitous across the industry. So if we're building models, let's take generically, we would start with some ER diagrams. We would look at our entities, our relations, our roles, and we would usually normalize that data after that. We would find the functional dependencies, transitive dependencies, go from first normal form, second normal form to 3NF, and usually we stop at 3NF, even though there's another 5, I think, normal forms out there as well. And once we have that, we would implement that into our database, and that would be it. So conceptually, what that means is that if you look at the database, you're dealing with 3 levels. So the first level is a conceptual level where we have our ER diagram. We normalize our data. We get to our logical model, and that's kind of where we stop, because that's been the promise, and that's the value, which is huge, of the relational model in SQL, which means that it creates the physical independence of Grackle, of data. And by the way, I'm personally, I love the history of how this tiny single idea in history changed the course of so much of software development. And I hope some of you share that geekiness as well. But so if that's the way we think conceptually about modeling in SQL, let's compare that with how we would do that in Graken. So we take our ER diagram. Let's say we've got some high-level conceptual model. And let's zoom into one aspect of that. So here we have a relation, a supervision relationship. We have an employee entity, and we have some attributes here. So the squares here denote the entity type, and the diamond shapes denote the relationship types, and the circles are attributes. So let's look at this model right here. And so how would we model this in Graken conceptually, without looking at the code just yet? Now this is where it gets exciting. It's a direct mapping to how we would do it in Grackle. What that means, the conceptual model is your model in Graken as well. Almost literally. So you can see here we've got roles, we've got an entity type, and we've got a relation and some attributes. I didn't put all of them because just I was trying to make the slide look pretty. So what that means, if we look back at our architecture diagram, if we're working in a relational way where we're creating some physical independence of data, if we don't have to go down to our logical level, what that means is we skip that part. So in a sense, we can say that we're creating some form of abstraction over that logical model where any query that we ask at that logical level, as long as the query is logically equivalent, the system should figure out how to construct all of the logically equivalent queries that you're trying to ask at that higher level. So let's look at how that looks with actual real data. So if anyone has learned SQL in a Microsoft environment, then I hope you're familiar with the Northwind data set. Is anyone familiar with that? Good, nice, have the room. It's a fictitious trading company with some fishery employee. There's some data from employees, from suppliers, products, orders, customers, and it's a great way just to learn how to do SQL. So let's look at how we would model things or how the actual code. So let's take one table, this products table. So we've got a product name, a supplier ID, category ID. So let's look at a simplified version of that. So if we've got our table here, if we've got one primary key in the form of a product ID, we have two attributes and one category ID as a foreign key. So in Graken, not all the time, but you may suggest that a table may correspond to an entity. So we say we've got a product entity. Then we say we've got three attributes, the product ID being the key. And then we've got the foreign key. So what do we do with the foreign key? So what we do see a lot, and that's something that I guess it's our responsibility to uneducate people to do, which is that some may model that as an attribute. Now, that's wrong, because conceptually, a foreign key, most of the time, you're referring to some sort of relation. So instead, you want to create a relation between some other entity type or a thing, some concept, that relates the relation to the entity, in this case, the product entity. So let's look at how that looks in code. So there's going to be quite a bit more code, by the way, just FYI, in case I was boring you. So we're defining a table. We're saying there's a products table. So we say create table. We define some attributes, the same as I showed before, some cardinality constraints. In SQL, in Grackle, this would look as follows. So we've got a product that's an entity. We've got also some attributes. We use the keyword key to denote it's a primary key. Then we say there's another three different entities or attributes as well. Now, there's two observations just to make real quick. So there's no such thing as a null value in Grackle. So if a thing, an entity, or any type of concept doesn't have an attribute to it, or some attribute value to it, it just doesn't have it, period. There's no such thing as a null value in that sense. And that implies that attributes are first-class citizens of the software, of the system, which means that if you've defined these attribute types already, I don't have to declare them again. But if you're just starting out and these attribute types haven't been defined, you would define them as well. And this is the notation that you would use. You would say, in this case, product ID, sub-attribute, data type double. Now, if we had the foreign key, so remember there was a foreign key as well. So we had the foreign key in our table that matches the categories table to the products table. In Grackle, that would look like this. So remember, we're connecting one entity with a relation to another entity. So we would say this product plays a role. It plays the role of product assignment. That's a word I made up, and you may choose differently, but let's use it for the purpose of this exercise. Now, if we haven't, so here we're declaring that a product can play a role of product assignment in some relation. Now, if you've defined the relation, you don't have to declare it again, but if we haven't, then this will be the notation to actually declare that relationship. So we would say the assignment is a relation which relates to a role, product assignment, and then the category would play the assigned category role in that same relation. So that's the end of the modeling part. So in the next section, what I want to look at is inserting and reading data relationally. So relationally, that just means using a SQL mindset point of view, looking at some of the standard operators that I'm sure we're all familiar with. And one of the things I want to keep in mind there is that the way we think about a question is actually very much the way we think about a question semantically, that never changed, right? If you want to know who your employees are, that's just a question. The way you write that query depends on what database software you implement. And so in the next couple of slides, I want to show how do we think about those queries conceptually without looking at the code just yet. So let's look at one. First, let's start with, let's say we want to insert a new product with product name chocolate. It has a product ID of 12, quantity per unit 421, and category name confections. I love chocolate, by the way. So we would first, because the categories table is a foreign key, so we need to fetch some sort of ID, some foreign key from that table. So let's say we do a select query. And then we would insert the row, the chocolate row, into that products table using the corresponding attribute values. So in Grackle, we would do it like this. We would say first, we would match. We do what's called a match insert query. So we would start by matching also the categories, the confections category. But instead of fetching the value, instead what we do is we assign, so we match for this category type, and then we assign it with $C. So now we've got a category, confections, assigned to that variable name, $C. So what we can do then is we insert that data. So you start an insert statement by writing insert, and then you say $P is a product. So now I'm inserting a new instance of a product. I'm saying that product has three attribute values: product ID, product name, quantity per unit. And to create the relation, I simply create a tuple between the two, and we assign a variable name, a variable here $R to that assignment, and we put $C and $P in that same relation. Oh, and that's how we would insert the data. Or you would commit it depending on what driver you use. Okay, everyone take pictures? Yeah, ready? One more there? Okay, great, next. So let's look at let's look at how we would read data. So in SQL, the standard way of doing that, select from where, which conceptually is actually, you first do the from, conceptually the from where select. So from which table, where restricted, and select which columns you want to read. In Grackle, the sort of equivalent would be a match get statement. So we match, first of all, we match for some form of thing. Usually you may restrict it by using some attribute value. The value of the attribute you can assign to a variable as well. And if you're now fetching for both this concept here and this concept here, we can say get $A or $V. Or if you just want the value, you just say $V. So, projection. I hope people are familiar with projection, but projection in relational is effectively we're just looking at creating a virtual new table out of a base table, given some select statement. So in this case, the question that I want to look at is, give me all the product IDs and product names. So a very simple question, which effectively you got your table, you create a virtual new table and just get all the columns from that same table. In Grackle, conceptually, you're not working with tables. So you're actually just you're just fetching the product, so the entity product, and then its two attribute values. And you would assign a variable name to an attribute, to both attributes, and then you say just get $PID and get $UP. I mean, I just made those up. It's UP stands for unit price, but you can make up whatever variable name you find useful. So that's projection. Let's look at restrict. So here we're looking for, give me a product IDs, product names for products with a unit price higher than 12.5. So in projection, in restriction, we're effectively creating another virtual table that has some restriction based on some column in a table, and we're creating we're creating a table out of these ones based on this restriction. In Grackle, that effectively is similar in a sense that we're thinking about a product that has two attributes, but one of those attributes has an actual value that we assign to. In this case, we just say the variable, the value of the variable of this attribute type is higher than 12.5. Union, let's look at a union query. So union queries, the question here would be, get all the different cities in which suppliers and customers are located. So effectively, any city that has suppliers and customers. Conceptually, you're just putting two tables together, and if they overlap, and also the ones that don't overlap, return me all those different cities, and you create a virtual new table out of that. In Grackle, the way we would think about such a question in terms of formulating the actual query would be by thinking about, first of all, we're looking at the city. So because we're fetching for the city name, we attach $CN as the value to be fetched. Now that's attached to a city, and then we say that city needs to be located, it needs to be connected through a located relationship to a customer, or that city has a located relationship with a supplier. If we then look at intersection, where we're looking for all the cities where both customers and suppliers are located, so only those that are both located in that city. Effectively, we're looking at a table that intersects between the two tables. Conceptually, that looks like this. So we're looking at again, similar thing. We're looking at a city with a name, so we're fetching this variable. That's the answer to our question. That's in a city, but the difference here is that this entity needs to be connected to both a customer and to a supplier. And then we fetch $CN. And finally, probably the most well-known of operations, which of course there's many types of joins, but here I just want to look at inner join, is give me all the corresponding category names for each product name. So effectively, we're just joining two tables, given some restriction, and creating a new virtual table out of it. Conceptually, this is quite different in Graken because what we're actually trying to ask is give me a category and fetch the category name by assigning it a variable name that has a relation assignment to another product and fetch me that category name as well. So I hope that was useful. But the really important thing for me to say is that, now first of all, if you're going to be using Graken or are using Graken, you're not using it because you want to write relational queries to it. If that's why you're using Graken, please don't, because it's just not going to work. It would work, but you want to get the value out of Graken by thinking differently. And sure, we're all familiar with writing SQL queries, at least I think so. But why would we use a tool if our use case allows us to do otherwise? And so with the previous question that I'm trying to show here is basically that the way we think about the question, if we can write a query that mimics the way we think about the question, we not only write better questions, but we also get more semantically accurate data back. And so with that, I want to go to the next section, which is how do we actually think about our data, both from a modeling point of view and a querying point of view, using the hypergraph and the automated reasoner under the hood. So, I pressed the other way around. So with that, I want to go back to our favorite Northwind table, Northwind. And and rethink this model. So this is what we do a lot, by the way, with clients, where they've got a specific schema, a specific set of tables, and they're very steeped into thinking that this is how it should be modeled, and they try to make a one-to-one mapping. But if you're doing that one-to-one mapping, again, you're missing the point of your efforts in using Kraken, because we appreciate the effort, but if you're making those efforts, let's do it well. So let's look at this data set again. And specifically, let's focus on these 5 tables. So if we think differently about the way we would model them, at least this was our effort. You may disagree, by the way. Please do afterwards. Happy to chat. We would say, let's say, we would create 4 entities out of them. And we would say, there's a company, there's an employee, there's an order, and there's a product. Then we would think, okay, what are the relations that we want to create between them? We say there's a sale relation that happens between an employee, an order, and a company. There's a stocking relation between a product and a company, so a supplier. And there's a containing relationship of a product that is contained in an order. We add the role players. So here you can see that a company can play both the role of customer and supplier, depending on the relationship that they're doing. The product plays the role of stock in that relation. We've got a contained product, a containing order, a placed order, and a seller. So the employee becomes the seller if they sell a product in the context of a sale relationship. Yeah, picture's done. And there's 2 attributes that we can add as well. And the reason I added these here, and obviously we should add more attributes here, is because I wanted to highlight and make the point that we add attributes to relations as well. In this case, we add here a quantity and a unit price. So now we have a very granular understanding of our orders, of our products, if we want to know this information and are querying for that. So let's look at how this actually looks in code. And by the way, I mean, we spent a lot of our energy and internal debates and fighting to make the language as simple as possible. And by simple, I mean as few characters as is possible. And that's not easy to make it as simple as it looks right now. And I wish we could share that passion that we have more, and I guess this conference is one way of doing that. Because as we look at this definitions right here, we see that we're creating an employee, which is an entity, a company, which is an entity, an order, which is an entity, and a product that's an entity. That's all I have to declare to create those entity types. Then we would create the relationships where we say sales subrelation. We denote all the role players in them by using the keyword relates. We have another relation, a containing relation that has 2 attributes and 2 role players. And a third relationship, which is the stocking relation with 3 role players. Now, as a final step here, we simply put these relations, these roles, and connect them to the corresponding entities. So for example, an employee plays the role of seller. Now, I just want to quickly come back to what I just mentioned before. We hope that as you read this schema, this ontology, that it's almost humanly readable. Because if we can do that, we give access to our models, our database, to a much wider audience than just people that are familiar with SQL or SQL type-based languages. So let's look at some queries, and I'm getting to the final stages of my talk right now. So let's look at the traversal type query. So these are queries that we're traversing through various different types. So the question here is, give me all employee IDs who sold to a customer in London that is of customer demographic X. X is just a variable placeholder. So conceptually, the question here becomes, give me an employee that has an attribute, some employee ID, that is connected through a sale relation to a company where the employee plays a seller role and a company plays the customer role in that sale relation. We make sure to say that the company has an attribute called city with the value London, and that has another relation to a customer description, and there we put the demographic and the value of that attribute as X. So how do we write that in both languages? So in SQL, we would define the table, and we just put a bunch of inner joins. In Kraken, we would first ask for the employee. since we want to get the employee IDs, we attach the attribute value to a variable, so we can fetch it later. Then we say $C is a company, has city London, so we're looking for a company that is in London. And then we connect them through a relationship. So we say $S plays the role of customer, sorry, $S plays the role of seller, and $C plays the role of customer in a sale relation. So now we've got that relationship nailed down. We go further, and we look at, give me a customer demographic that has customer description X. And we attach that to a variable name here, CD. And then we put them in a tuple as well, so then we fetch that attribute value right here, EID. So let's think how we could extend the model as well. Let's say Northwind becomes a big company and it needs to extend its database. They've been through some M&A and they're now selling to different types of companies. So we can create a type hierarchy of companies or organizations where the super type is an organization and it's now selling to both for-profit and non-profit companies. And let's say they also have different suppliers or companies or customers that are banks and are pharmaceuticals. Again, just a thought exercise. So this is really useful because if I'm now interested give me all the banks, I can just write and explicitly ask for all the banks, or I can query for the super type, the organization, and I can get all of these entities rather than asking for give me the bank, give me pharmaceutical, the for-profit, the non-profit, depending on how you've modeled the data. The way we would write this would be as follows. So we define organization sub-entity, as we've been doing. And then we say for-profit sub-organization and non-profit sub-organization as well, where now this subtypes this type here. And we can go further, where we say a bank is a sub-for-profit and a pharmaceutical sub-for-profit as well. And so these 1, 2, 3, 4, 5 lines is all I have to write to at least just create those entity types. Isn't it great? So another type of reasoning is the rule-based reasoning. And I think Heiko had already this example in a slide, so it's useful as a reference point. And if I know that if X is located in Y and if Y is located in Z, then I also always want to make sure that X is also in Z, which from a querying, from a rule writing point of view, we can simply write as creating in a when statement, if X is connected to Y, playing these roles, and if Y is connected to Z, then X also connects to Z. Now this is an interesting example of a rule because when I was looking at this data set, there's an interesting couple of tables here where if I know that my employee is in a territory and if that territory is in a region, if I want to query now, give me all my employees that are in a specific territory, in a specific region, I can effectively leverage that rule to get a more simplified question, or effectively just ask a higher level question. So if we're looking for, indeed, give me all my employee IDs who are in a region with region description X. So in SQL, we would ask for the employee table with the employee ID. We do some inner joins to traverse through those three tables. But in Grackle, if we have that rule, we can simply say if $R is a region with a region description X, we have also an employee that has an employee ID, again, variable name EID. We simply say they both are connected through a relation. And although that's not actually existing in the database, if you have your schema set up in such a way, the system would simply reason that for you. And so we just simply said get EID and you get that question. So here, in this very simple example, we see how some of the logic allows you to write conceptually simpler queries. So to take that example to a slightly more advanced use case, where if you know that give me all organization IDs of any type of organization that employees have sold to who are in a region with region description X, for simplicity's sake, let's say in this domain, in this company, in this database, there's two types of organizations, a company, and charities. Now, given the original data set that we saw before, if we were to think about the actual question, what this means, if you were to write the actual explicit query path given the persisted data, you would say both charities and companies are connected to orders, are connected to employees, and are connected to territories in a region with a certain variable value. You would have to explicitly declare both query paths, which in SQL would basically mean a bunch of inner joins, union, and a bunch of other more inner joins to mimic those two types of queries. And so when we think about how we can get value out of using Grackle here, in this case, we would simply say, again, we get the organization with the org ID, we get the employee, we put them in a sale relation, we get a region with a certain description, we connect them in a relation as well, and then we just fetch the $CI. So I hope that is piquing your interest on how pushing down some of the logic into the database allows you to ask more higher level questions to the database. And to us, to be fair, it's not really about counting the lines of code in terms of difference, because sure, you may create a view to reduce your number of queries in SQL, but the point is that most of the time, actually, the person making the model isn't the same person asking the questions. And the person asking the question to the database may not necessarily know the full model. So if you can abstract that whole model itself, you enrich and empower a whole new people inside your organization to ask questions that allow you just to build better software. So I hope this is interesting and this is useful. So, and we can take this more extreme to actually, look at a really long as SQL query and look at how this looks in Grackle. And again, it's not about counting the lines of code necessarily, but it's a useful reference point to make the point here. And again, there's more logic behind here, but if we leverage the reasoner, the hypergraph, there's a lot of simplicity that we enable by creating that abstraction layer, which goes back to what I said before in terms of the architecture. Because we want, and Kraken is that logical abstraction, over the logical model. So to end effectively to go full circle, Grackle in that sense is a language that allows you to read and understand intuitively, where you can ask questions at a higher level while letting the system figure out how to do the lower level operations. So with that,